Sometimes we have research questions that you might not expect from computer scientists, like can we illuminate individual neurons, or can we see through forest? And about 6 years ago, we had another such a question, and that was, can we build a 1 millimeter thick film camera? And that is what I would like to report on today. So can we build a camera that is flexible, scalable, transparent, just like a plastic film? Supposing to do the same like a normal camera would do. What the heck is that good for, you might think? It's not good for taking images like you would take with your cell phone. It might be good for representing an advanced sensor, like touch sensors that we use in mobile devices, without limitations that these sensors have to be planar and have to be touched, because our sensor can have an arbitrary shape and it can see objects that are in front. So we don't have to touch it. That's the motivation, and we're not alone with that motivation. There are a couple of other groups internationally that work on curved cameras with different approaches. So here's one example that uses normal photodiodes that are connected with a flexible wiring to enable curved image sensors. Our approach is very different, and I would like to explain you very quickly how that works. So basically, we use a plastic film that contains fluorescent color particles. Fluorescence works like this. It takes a light source, a wavelength. We have a blue laser here, and it basically absorbs that blue light and emits a longer wavelength, green light in this particular example. And since the light emission happens inside the film, the emitted light is transported mainly inside the film and leaves the film at the edges. Most of the light leaves the film at the edges. That's why the edges are so bright. So for us, this film is really like an efficient 2D light guide. And the question is, like you see in this image here, if we focus an image on that plastic film, can we, from the light signal at the border, can we reconstruct that image? So if you consider that there's a single point of light emission, for example, at that position here, and we know that light is transported radially in all directions inside the film and loses intensity over travel distance. If we make measurements of that light signal that arrives at the border at different positions, can we reconstruct where that point is and what intensity it has? And actually, for image reconstruction, that is a little bit more complicated, because we are dealing with a really messy light signal, because we have to reconstruct not only a single point, but many points. Every pixel is its own point at different positions with a different intensity. So we have an overlap of different individual light signals that we measure, and the question is, can we reconstruct that? So again, we measure the light signal at the border, and we want to reconstruct the image. So 6 years ago, we started with that challenge. The question was, is that possible? Talking to friends in physics, the answer was no. Talking to friends in mathematics, the answer was no. And we were a bit more optimistic in this case and simply tried. So we basically built a prototype that uses this sensor, this film. We connect photodiodes at the borders. We project that image focused on the surface, and we try to reconstruct an image, and that was our very disappointing first result. So an image that has only 4 pixels, actually this image is supposed to be this. And that's, of course, not really a good quality that you would expect. So, but we had I think a key idea in the project, and the key idea was that we do not measure this messy light signal directly, but we multiplex it into a more structured signal by cutting out small triangles out of the film at the border. So the pink triangles are cut out. So material is missing, and because material is missing, that triangle would block light. And what is left are other triangles here that would pass light through a small opening. This is such a triangle under a microscope. The light has to go in through this opening. This is cut out, this is cut out, this is left. And what you see at every position at the border of this triangle is the light integral through the film only within a particular direction. So we multiplex the light signal per triangle in 2 directions, and we do that at many positions at every border of the film. So we have many of these triangles, so you can consider each of the triangles to be a simple 1D pinhole camera that sees a simple 1D image by looking through the film. And we have many of these pinhole cameras everywhere. We as a computer scientist would call this signal a light field. It's a 2D version of a light field. We normally deal with 4-dimensional light fields in our group. This is a 2D version. A mathematician would call this signal the Adhan Transform of the image, because that's really what it is. We measure line integrals of light through the film, and that's pretty much what like a computer tomograph does. We do this with optical light, with visible light here. A computer tomograph does it with X-ray radiation. So having understood that, so here you see a simple prototype with a point light source that produces the signal here. We use optical fibers to transport the signal to sensors where we make measurements. You see this very clean structured signal. The question is, if you understand that this is the Adhan transform of the image, our image sensor does not measure a normal image, it measures the Adhan transform of the image. Reconstructing the image would be finding a solution to the inverse Adhan transform. And luckily there are many options to do that. Mathematically, we can, for example, use tomographic reconstruction for image reconstruction. That would be the result of a tomographic method, which is better, but still not good. The reason why it's not good is that a mathematical description of the inverse Adhan transform would basically not contain any information about small manufacturing mistakes that we make when building the sensor. So another key idea in this project was to not describe this inverse Adhan transform mathematically, but to learn it with machine learning. We use many thousands of images that come from public image databases like Flickr and train the sensor to learn how this inverse Adhan transform looks like. And with that, we get significantly better result. That is a research overview over the first years of the project. In 2013 and 14, we could do grayscale imaging. So this is ground truth, this is what we can do in real time, and this is what we can't do in real time, where we need a little bit more processing time to get better quality. 2015 and 16, we did color imaging by simply stacking multiple of these films on top of each other that are sensitive to different wavelengths. The top film, the green film, reads blue light, the red film reads green light. Fluorescence is not really efficient when it comes to absorbing red and emitting infrared, so we don't do this physically in our sensor here. But as you see in these results, we are still able to reconstruct a red color channel, although this is not measured physically. That is achieved again with machine learning. We simply learn the correlation of a missing color channel when two color channels are given by looking at many thousands of existing images, and that works surprisingly well. In 2016, we could do 3D by simply taking the film and wrapping it around a 3D object. I have to admit we apply a trick here. We have to illuminate this object with a known speckle pattern a couple of times, and the light that's being diffused from the object and recorded by the film can give us information about the 3D shape of the object using compressed sensing. So this is a laser scan of the object, and that's what our sensor can see. The problem so far is, when we think about a camera, that this is really not a camera, this is only a sensor. What is missing for a camera is the optical imaging component, what a lens would do in your normal camera to pick up the image of an object at a distance and focus it on the sensor. So here we have an image at a distance. This is our sensor covered with a piece of paper to show you what is the optical image that our sensor sees, and you see without any imaging optics, that image would be completely blurred, and that is what we would reconstruct. The goal of the LIT project now is to find a solution that can be used with our sensor to do what a lens in a normal camera does as a flat film. So again, our goal is a 1 millimeter thick camera. We have two sensor layers, each 300 microns thick, so there is 300 microns left to implement this lens, without using a lens, obviously. So the basic idea is that we need some thin film optics that shapes light in such a way that a machine learning technique can reconstruct a focused image from that shaped light signal. So the project or the challenge is twofold: finding this thin film optics that is suitable and finding the machine learning technique that can do it. So this is a research overview again. We started classically with coded apertures. A coded aperture is, in our case, a binary mask pattern that consists of transparent and opaque pieces. in a very structured way, so that when light passes through this mask, it is shaped in such a way that we can computationally reconstruct a more sharp image with a larger depth of field for our camera. So this is ground truth, and this is what we get. Not very good. So again, in this case, the images are reconstructed for objects at a distance. The reason why that doesn't work well for coded apertures is that coded apertures require a sensor resolution significantly higher than the resolution of the mask pattern. Our sensor has already a relatively low resolution, so we would have to go down with the mask resolution of the coded aperture even more, and that leads to relatively bad results. Another approach that we did last year is to borrow an idea from X-ray imaging. We use something that is called a solar collimator. A solar collimator is simply a grid of holes, with the idea that that grid of holes lets light pass through only when it comes in a mainly perpendicular direction. If the direction has a more steep angle, it will be blocked. So the idea is if we have such a very thin solar collimator, 300 microns thick, as a layer on top of our two sensor layers, we would increase depth of field, but of course we would lose light transmission because this is not very light efficient. It blocks a lot of light. Here you see a prototype that is built with a 3D printer, not nearly the scale we desire. This is about 1 centimeter. We are thinking about 300 microns again. But this is, as a proof of concept, the results that we get compared to what we get with a coded aperture. At a distance, object as a distance can be reconstructed with a larger depth of field, would be more sharp than without such a layer. To improve the light efficiency, this is what we did this year, is that we add a micro lens to every aperture opening. So this would be something like a micro lens aperture array. Every micro lens in these aperture openings would collect more light, and that gives us actually a much better signal-to-noise ratio. So that is the quality that we can achieve at the moment with a good signal-to-noise ratio and a relatively good depth of field. The question is, what about that 1 millimeter? So again, these prototypes are 3D printed. We cannot achieve a high resolution with today's 3D printers. We need another manufacturing technique to achieve 300 microns. This is what we did with the Karlsruhe Institute of Technology. This is our collimator integrated into polymer using an X-ray lithography technique. One thing that you notice is that the aperture openings are hexagons, no squares anymore, because a honeycomb structure is the most light efficient structure you can think of when you think about tiled grids. So this layer, this is the wafer, is 300 microns. We have now a camera that is 1 millimeter thick, doing all the things, the optical imaging and the sensing. The disadvantage of this prototype is that the ratio of the wall thickness versus the hole openings is really bad. So we have 25 microns here, wall thickness, and that would block a lot of light. So this is the second prototype we are working on in Karlsruhe. At the moment is only the mask for the collimator that will be produced in an extruded version later, again 300 microns, but in this case the size of the walls are 5 microns. This is where we are, and the question is, how would you make this more efficient by integrating some lens optics at that scale? So again, we are at the micrometer range here. What technology exists that allows us to integrate refractive optics to collect more light? If you have any idea, let me know. We didn't find anything so far that allows us to do that at that scale. What might be an interesting alternative is the recent development in meta lenses, meta surface that consists of nanometer scale metallic antennas that basically would shape light when it passes through, just like a lens would shape light. So using meta surfaces, we can build lenses that are nanometer size thick, and that would be, of course, an interesting option for our project. I'm not sure how cost efficient or how cost intensive the production of meta lenses would be at that scale compared to a micrometer range scale, but that would be an interesting alternative for our approach. So with that, I would like to thank you for your attention.